On behalf of our institute, it's my pleasure to introduce Professor Cédric Villani, who is going to deliver the talk entitled Optical Transform in Geometry, Monge meets Riemann. Professor Villani is the director of the Institute Henri Poincaré, professor at the Université de Lyon, both in France, and a recipient of the Fields Medal in 2010. It's of course a honor for us to receive him at our university. This lecture is part of a series of masterclasses sponsored by IMPA, and I take the opportunity to thank Professor César Camacho and Jacob Pallis for the opportunity to have this particular one held at our institute. Finally, I would like to register the presence of Professor Adnei Melges de Andrade, Executive Vice-Rector of International Relations of the University of São Paulo, and express our gratitude to this office, as well as to the General Consulate of France in São Paulo for their support. Thank you.
Thank you very much. Everybody hear me well? Yes. Okay. It's a great pleasure to be here. This is my first trip in Brazil. So I was in Rio before, now I'm here. As was mentioned in the introduction by Professor Cordaro, this is part of the Magna lecture series of IMPA. So it has been centralized and organized by César Camacho and Jacob Pallis. And it's a pleasure to thank all the people involved here for the excellent organization. Today I will talk about optimal transport and curvature. As I said, Monge meets Riemann. Another possible subtitle would be this: from economics to physics to geometry to economics. With one important idea is that often a tool or a recipe or a mathematical method can make a journey from one field to the other. And it can be extremely fruitful, this interaction and the meeting of various ideas. It will be the opportunity to talk of several different topics. At some parts, the talk will be slightly more technical than others, but anyway, even if some parts are technical, it's the main flux of ideas that counts. And I will insist not only on the ideas, but on the people who developed them, so there will be some history and some heroes. The first of these heroes is Leonid Kantorovich, whose 100th anniversary is celebrated this year. Leonid Kantorovich was a great man, a Russian scientist, outstanding mathematician, and one of only two mathematicians who received the Nobel Prize. Together with John Nash is the other mathematician who did receive the Nobel Prize. Leonid Kantorovich was working at a time and a country in which everything had to be planned. And even for those who disagreed with the methods used by the communist regime of the time, the idea of planification was important. And that's what Kantorovich used and worked on. His first important work, very important work in this field, was this 1939 work on mathematical methods of organizing and planning production. Of course, at the time in which production was a critical thing, war was coming. In 1959, he summarizes his economic work in his masterpiece, The Best Uses of Economic Resources. In 1975, he obtains the Nobel Prize in economics. Kantorovich, on his own, symbolized very well the dual nature of mathematics, both abstract and concrete. And he worked on very abstract subjects like partially ordered spaces, but also on numeric approximation, and on very concrete problems of organization. Nowadays, we would call them operational research problems. Dispatching plywood to cutting machines was one of them. I will come back later. But also railroad transport or atomic bomb is a project on which he worked. Cars on the life road. This is the kind of applied problem that you had to solve in those days. During the war, there was the siege of St. Petersburg, and the only way out of the siege by the Germans was to fly by means of water. This was so cold, of course, that you had this ice on which the cars can drive. You want to have people flying from the city as much as possible. So the most cars you can put, the best it is. But if you put too much cars, the ice will crack and it will be a disaster. How much can you put? This is a kind of problems that mathematicians, applied mathematicians of the times had to solve. And this was important. Second World War was gained in large part on science and specifically on mathematics and theoretical physics. This was a part of it, but without people like Turing or like the people who worked on the Manhattan Project von Neumann and the others, maybe the Second World War would have been completely different. On a lighter tone, Kantorovich worked on taxi fares and improved radically the taxi fare system in Moscow at some point. This was confirmed to me by some Russian friends. This is the secret note that the CIA hold on Kantorovich. Internationally recognized creative genius, etc. Why does CIA put a note on Kantorovich? Of course, because they understood it was such an important weapon, such an important strategic thing to have a very great brain at disposal. In one day, this is the plywood story. Plywood is something like this, right? You cut the trees, you make thin slices, and you patch them together to obtain something that you can use to construct a table or whatever. And one day, these people from the plywood industry, they come, some plywood factory, they come to see Kantorovich, who was young but already the head of his department. And they explain him, we need a mathematician to help us solve some problem. We have a number of trees that we exploit from here and there. We have machines that cut the wood, machines that assemble the wood, etc. And we have many possibilities. We don't know if we have to put 50% of our production there, 25% here, etc. According to the total amount that we can cut, according to the fact that some trees are hard and some trees are soft, etc. How can we compute the best possibility? So many possibilities. Kantorovich worked on this problem and found an abstract way to rephrase it. And this was 1939, the birth of what is now known as linear programming, one of the most successful operational research algorithms ever designed. Kantorovich was not the only one to develop linear programming. At the same, it was also developed by Danzig and Koopmans independently. Both Kantorovich and Koopman received the Nobel Prize. Danzig did not, for reasons that nobody understood. Linear programming is a very general setting in which you have some unknowns, xi parameters like percentages of your production or whatever, and you want to maximize a linear combination of these xi's. So these coefficients ci's are given, and the xi's are the unknown, and you want to maximize a linear quantity under some constraints, because always you have limitations on the resources that you can use or the prices that you can afford. And if these constraints are also written in a linear form, like this, with linear inequalities, the xji's here are multiplied by these coefficients, then you have a linear programming problem. The geometric representation would be this one. This is the space of parameters. For instance, product M1 here, product M2 here, one product and the other product. And you look at all the constraints. For instance, you are unable to produce more than 4 units per day of the product number 2, and then you have this constraint that it has to be below this line. Or you can you have a certain constraint that the 2 times the first quantity plus 2 times the second quantity should be less than 14 units, etc. And this defines an admissible region, and among the points in this admissible region, you want to see which of the corners will be the best for the output that you want. This problem is very elementary. I remember vividly doing exercises like this in high school, which were quite fun. I don't know if it's the custom here too. Okay, I see some people saying yes. And this, I think, is really nice. At the same time, it's simple, but it's so powerful. When you are in high school, you solve it like you just work out. Like, for instance, if I have something representing the slope that I want to optimize, I will slide it until I hit the maximum point. But in real life, you can have hundreds of parameters or thousands. And people who use linear programming for all kinds of purpose have to solve these problems. When you buy a ticket, a train ticket, the price has been computing with some linear programming algorithm. Often the water networks are computed with linear programming. Here, from some tutorial, I extracted some of the exercises for some students in economy based on linear programming. Okay, I see people out there. I don't know if they can enter. You tell. Okay, okay. So, product mix problem. You see here 3 parameters, how many of each type of tie to make per month. I like this exercise. Here it's about advertising. Here it's about how to blend the grains inside some cereal. Each type you have some unknowns, some constraints, and you want to maximize profit or maximize audience or maximize interest or minimize the cost, you know, things like this. These are all examples of linear programming, and any student doing a bit of advanced economy will have a course on this. You see, of course, it doesn't have anything to do now with the plywood, but the abstract version of the problem is everywhere, as usually in mathematics. And we have softwares now, many softwares that compute it automatically, the solution, using different algorithms. Of course, the fact that you have the software, if you're an engineer, does not get you rid of understanding the mathematics that is behind. And you have to know in which situation the software will work well or not well. It will depend on the conditions. Some of these algorithms are very nice. And there is a nice interplay between the economics and the mathematics. Also, in an interesting twist, it goes in both directions. We are, okay, I will talk about this later. Before I continue on the algorithmic issue, let me mention this historical coincidence that Kantorovich, working on the linear programming and on this plywood stuff, recovered a problem that had been asked by Monge a long time ago, long time before, at the end of the 18th century. This is Gaspard Monge, one of the great mathematicians in France at the end of the 18th century, very well involved in the revolution and creation of some important schools of engineers and scientists dating from this time, like École Polytechnique, personal friend of Napoleon. Monge worked on this problem that is known as théorie des déblais et des remblais, that nowadays we call optimal transport problem, an area in which I worked. A problem which now is named Monge-Kantorowicz in honor of both Monge, who first formulated it, and then Kantorowicz, who devised the first modern theory allowing the algorithms and so on. Here is an abstract formulation of this Kantorowicz problem. Take two complete separable metric spaces. If you don't know what complete separable means, it doesn't matter. The fact even that these are metric spaces, it's just we want to be able to do probability theory on it and have probability measures. Now, mu and nu are two statistical distributions, two probability measures, one on the first space and one on the second space. And you give yourself a cost function, which is a function of one variable in x, one variable in y, a real valued function. And you think of it as the cost to go from one point of the first space to the other point of the second space. Like I have material to transport, and how much will it cost to transport? Now, this pi here, capital pi, will be a set of joint probability measures on the product of x and y. And we look at all probability measures in two variables whose marginals are given by the first measure here and the second measure there. Marginal means that you integrate on one factor or the other, so that it's as if you are forgetting the other space. The technical definition is that if you look at a function depending only on x and integrate it with respect to pi, then it is as if you are integrated with respect to mu, variable on the first factor. Another way to say it is that it's the image measure of the probability measure under the projection. If this is my space x, and this is my space y, and this is my probability measure, when I integrate in this direction, I obtain a probability measure that should be mu. And if I integrate in that direction, I should obtain nu. This is marginals. Now, after this setting, I can define the Monge-Kantorowicz problem in the way that Kantorowicz formulated it. We are minimizing over all admissible joint probability distributions, pi, the integral of the cost function with respect to pi. Look at this. Okay, it's a bit more complicated than what we saw before, but the unknown is pi. This is an integral. So this is linear with respect to pi. What are the constraints? And I am optimizing a linear function of pi. What are the constraints on pi? It should be non-negative because it's a probability measure. It should have integral 1. It should belong to this set. But all these constraints are linear with respect to pi. So we have a linear programming problem. This is exactly an application of it. Only difference is that it's infinite dimensional because you have an infinite number of degrees of freedom for pi. So you can apply to it linear programming. In probabilistic version of the optimal transport problem, it's very simple to state. You are given two random variables, that is the law of x is given, the law of y is given, and you want to optimize the expected value of the cost to go from x, which is random, to y, which is random. Of course, when you specify the law of x and the law of y, you don't specify the joint distribution of x and y. Maybe they are strongly correlated, maybe they are independent, maybe it's in between. There are many possibilities. In the particular case in which the cost function is the negative of the scalar product in Rn, in the Euclidean space, then what we are looking in this problem is the same as maximizing the expected value of the scalar product between the random vector x and random vector y, which is maximizing the correlation. It's very natural. I see one random vector, another random vector, and I try to realize them in a way that they are as correlated as possible and try to find a relation between them. So this is the Kantorovich problem, viewed by a probabilist, and now viewed by an engineer is assume you are making some construction and you are extracting some material from some place. This is probability measure mu, this is probability measure nu. This is prescribed, and this is prescribed too. And now you will transport the matter from points here to point there. What are you going to do with the mass? Mass starting here, will you send it here or here? This one, will you send it here or here? You want to do like an engineer. This is x, this is y, and here this probability measure tells you how much of x you will put into y. Think of this as a probability measure with various intensities. That's your unknown, the plan of transport, and you want to devise it in such a way that the transport costs as little as possible, where the transport of each unit is given by your cost c. So that's the Monge-Kantorovich problem. Given the initial and final distributions, transport matter at lowest possible cost. If you think in discrete terms, this can be thought of as an optimal matching problem. The production, for instance, you have some factories that produce some goods here, and you want to send them to supermarkets where people will buy them. The factory, you want to send stuff to a supermarket that is not so far. Then what do? Do I split half of the production of this guy to send it here and the other half here? Do I put all the production of these 2 units there, etc.? If you want to optimize the transport of your goods, you have to solve such problems. If you are in front of this problem, how do you compute it in practice? So it's an economic problem. Kantorovich found this beautiful duality relation, which is still an active research area, even though it's mostly understood. Computing the optimal cost is like solving a dual problem in which you are computing an optimal pair of prices. Here you want to minimize, here you want to maximize. And here the unknown are some probability, here the unknowns are functions. You can think of this in duality. The function, the unknown here is a pair of functions, a real valued function of x and a real valued function of y. And the constraint here is that whenever I look at phi evaluated at y and I subtract psi evaluated at x, it is bounded above by the cost to go from x to y. And given that, I want to maximize the difference of the integrals between phi and psi. There is an economical interpretation. This is known as the shipper's problem. Here is how you can think of it. Imagine you are an industrial guy and you have these units of production and you send them to supermarkets as before. And you know how it will cost to transport the good from here to there, etc. And then arrives another guy who wants to be the intermediate. And he says, I will do the transport. Don't worry to compute. I will do it. I will buy the goods at the factories and I will sell it back to your supermarkets. And what we will fix together are just 2 prices. At X, the price at which you will sell me the goods, psi, depending on the position of the production unit, and there is a price at which I will sell the good for you back at the supermarket, phi, depending on the position y. And you see here, with this interpretation, this quantity is the profit that is made by the guy, or at least the amount that you will pay to this guy. Whenever there is something that you buy or something that you sell, it's taken into account here. So you see, he has an economic interpretation, and the duality says that if the guy is clever, he will take from you exactly as much money as you would have spent by doing the transport yourself in an optimal way. And this interpretation here, the constraint, is precisely that in order to convince you, he says, you know, you will not lose money the way I will do it, because the difference of prices will always be bounded above by the transport cost. Okay. This kind of interpretations gives you a flavor of what Kantorovich was working on and the fact that there were economic applications. It was extremely dangerous what Kantorovich was trying to do at the time, I mean seriously, because he was developing a rational theory of prices at a time and a place in which the notion of price was filled with ideology. In Marxist economy, there is a special price is something that is charged with ideology, and people in charge of economics in Russia these times were not so clever as Marx and not able to tell between difference between value and price and this kind of stuff. So it was forbidden to talk about the theorems of Kantorovich in public. Really. They would use all kinds of things and so on. No. But Kantorovich had this in mind. He was convinced it was important that he do this, because without a good theory of prices, the whole economy would collapse. This was time of war, economy was critical. In an interesting twist, sometimes the interpretation in economics can be used for the mathematics. We used to think that when you work in social sciences or whatever, or economics, the mathematic theorem will help you devise the behavior of the people. But sometimes it's the contrary. Taking this example, taking inspiration from the behavior of people, you get an interesting algorithm. This was found by the Greek mathematician Mitri Bertsekas in 1979. Auction algorithm. Here is the idea. This transport problem, think of it like there are people having various jobs. This guy has a job here, this guy has a job there, etc. And they all want to get good homes. A good home will be a home that is not too expensive and that is not far from the workplace. Otherwise, they spend too much in transport cost. So they will be competing to get the best homes, these N agents. Think of this as an abstract problem. Then on your computer, you have N points, whatever, but think of this in this way. And to start with, you put a pairing which is arbitrary between this guy here, this guy there, and the prices that are arbitrary. And of course, the people are not happy. This guy here says, this guy has a home I would like his better because it's closer to my office. And I'm ready to pay more than this guy. So the homes are put to auction. And each of them, in turns, if he sees he can afford something more attractive that taking into account the cost of that other home and the fact it's closer, the amount that is spent in the end will be lower. So he makes an auction, and he doesn't make a small auction, but a rather large auction to be sure that the other guy will not immediately make a higher bid. And this is the algorithm. You really do like this, and you repeat, and each time one agent is unhappy, he will make an auction and so on. And if the parameters are well calibrated and you do it with the right procedures, it will converge to the optimal pairing. It is fun that to make it converge, you need to impose some rules that are really used in auctions. Like there should be a minimal bid, a minimal auction by which you, a minimal increase that you're allowed, things like this. This and other algorithms allow to compute approximations of optimal transport. Now, thinking mathematically, what can we say about the properties of optimal transport? Always, to have a good understanding, you need to work on both sides, computing and understanding theoretically. Let us go back with the history of Monge and insist that there is a small distinction between the way Monge formulated the problem and the way Kantorovich formulated the problem. Monge did not look for a probability measure, a joint probability measure. Monge looked for a transport map. Both are equivalent if we are looking for a probability measure that is concentrated on a graph. a probability measure that would be like this. It meaning that you never split the mass coming from one place. One unit of production has to be paired with one supermarket, not with 2 or 3 or whatever. This is the way Monge formulated it. Now if you take a deterministic coupling like this, concentrated on the graph, and you plug it in the formulation of Kantorovich, you obtain this one. Infimum of the integral of the cost to go from x to y, and y is a function of x. And the unknown now is t, is the graph, not the measure. And the constraint is not the marginal condition, but the condition that the push forward of mu by the transport should be equal to nu. Push forward, I recall the definition. If you have 2 probability measures and a measurable map, the push forward of the measure is another measure if for any measurable set, the measure of the inverse image is equal to the measure of the set of which you are taking the inverse image. It is exactly equivalent to impose that you can change variables from one measure to the other, so you have the formula of change of variables. If you are a probabilist, you think, of course, it's very easy to understand. Push forward or image measure is just a change of random variable, going from one random variable to the image of that random variable by the map T. And for probabilists, this Monge problem is not particularly interesting to study, maybe. But for an analyst, it is a bit scary, because we all know when we make changes of variables, Jacobian determinants arise. It's hidden in the change of variables, but if we want to compute, we have to take into account this Jacobian determinant. And the resulting equation, if these, for instance, f and g are the densities of the first and final measures, you have to put here the Jacobian determinant of the map T. Now you look at this equation, at this constraint, and you see that it's very nonlinear constraint on T. We are not in a linear programming problem anymore, and it's much more complicated. So people did not really understand this problem for a long time. And to make things worse, Monge chose a cost function which looks natural, but was very tricky, the distance function. Distance is degenerate because, for instance, it's a convex function, but it's not strictly convex. And it took a long time even to prove that there is a solution to the Monge problem, that is, that there is an optimal transport. It was only at the end of the 20th century that this was solved. As we know, things get better when we are, like in integration theory, much better properties are obtained for the L2 Lebesgue space and for the L1. Or in geometry, looking at scalar products, Riemann geometry, etc., makes things better if we use quadratic things. It's the same in optimal transport. Instead of the cost of Monge, which is the distance, let us put the square distance in Euclidean space, a quadratic setting, and things will improve much. This is the first instance, the first cost function for which a good description of the solution of the problem was obtained in the 80s. And here is a theorem, very simple and nice, that was proven by various researchers, Brenier, Ratchev, Cuesta, Matran. If you have a density, if the first measure has a density with respect to Lebesgue measure, the start measure, then there is a unique solution of the transport problem. It is both the solution of the Kantorovich problem and of the Monge problem. So it's a transport map, and it takes a very special form that it's a gradient of convex function. A gradient of convex function is a monotone map in a rather strong sense. Of course, gradient of convex function is, if you take the derivative, it gives you the Hessian of the convex function, so it's non-negative. This is interesting in itself because it gives you a strong geometric characterization of optimal transport. that then can be useful in some algorithms. But also the output, even without thinking of Taylor transport, is interesting. It gives you a canonical way to construct monotone changes of variables, which are a very powerful tool. Changes of variables we know are powerful. Sometimes it solves your problem in a miraculous way. Monotone changes of variables have a particular status in geometric problems. To illustrate this, let us consider the oldest variational problem in geometry, the isoperimetric problem that has been around for thousands of years. And you take a volume that is given, and you ask what is the way to rearrange this volume in such a way that the surface is minimal. Volume we measure by the Lebesgue measure. Surface we measure by the Hausdorff surface measure, n-1 dimensional. And we all know the solution. Solution is the ball. This is, you think of the bubble like when you make soap bubble or whatever. Solution is the ball, so if the ball here has the same volume as omega, the surface here is not more, is not less, is not more than the surface of this. There are many proofs of this. One particularly beautiful proof goes by monotone change of variables. It is not very well known. Let me sketch it. I will cheat just a bit, and it will take just a few lines. Take a change of variable from the ball to your set omega, or from your set omega to the ball. For the moment, you don't assume any relation between the ball and the set omega, and we look at uniform measure. And you take a monotone change of variables, so the Jacobian matrix of the transport T should have non-negative eigenvalues, like the one I showed you before, which was a gradient of convex function. If you look in terms of density, the density of the first measure is just the inverse of the volume. It's uniform measure on omega. And the same for the target density. Now the inverse of the volume of the ball. Write the Jacobian equation. Determinant of dt will be then the ratio of the volumes. It will be a constant. And let us integrate this identity. First, let us apply the Jacobian identity after raising to power 1 over n. The Jacobian determinant is the product of the eigenvalues of the Jacobian matrix. These are non-negative, so this is a geometric mean. It's bounded above by the arithmetic mean. But the sum of the eigenvalues of the Jacobian matrix is the divergence of the map T. And when we have a divergence, we like to integrate. So let us integrate. This is a constant, so integration will just multiply by the volume of omega. And after I've integrated here the divergence, I apply the Stokes formula, and I obtain the surface integral of the transport map scalar product with the unit normal. The unit normal has norm 1, and the transport has norm bounded above by 1 because it's valued in the ball. So I can bound this by just 1, and this becomes the integral of 1 over omega, which is the measure of omega. Look, we obtain this relation between omega and the in volume and its surface. And for the ball, it will be easy to see that there will be identity. So this inequality is the isoperimetric inequality. This brilliant scheme of proof was devised by Gromov. And it is not an accident. It is a powerful scheme of proof. Quite some time after Gromov, together with Cordero and Nazaré, we showed that you can use the same style of arguments to prove more subtle inequalities, like Sobolev inequality. Let us do it. If you work in partial differential equations, Sobolev inequalities, you use them all the time. You find them in the textbooks. Sobolev inequality tells you that if you have a function whose gradient is p integrable, then the function itself is better than p integrable. It is p star integrable where the exponent p is bigger, p star is bigger than p. This is for all exponents between 1 and n. And to prove this inequality, there are various methods. One of them goes by change of variables, as we show. To prove this without loss of generality, you reduce to the case where u is non-negative valued function, and where u to the power p star has unit integral, so that this is equal to 1. And then your problem is to show that this is bounded below by a positive constant. So I take a function u satisfying this, I look at the LP norm of the gradient, is it bounded below? How to prove this? Let us pick up another probability density, whichever you like, and make a change of variable from u to the p star to that other probability density. And write the change of variables formula. And then look what I do. I look at the integral of g to the power 1 minus 1 over n, and consider this as the integral of the test function g to the minus 1 over n against g. Because it's this integral, I can change variables and replace it with the integral with respect to p star, to u to the p star. And there is y becomes t of x. After this, I use the Jacobian formula to replace g of t of x by an expression involving u and the determinant, the Jacobian determinant. And here it is. And now, because this is a determinant to power 1 over n, it's the geometric mean of the eigenvalues, I will replace it, bound this above by the arithmetic mean. And this will make a divergence appear, just as before. Now I have integral of a divergence test with something. What do? Integration by parts. We always like to do integration by parts. It's so powerful. So it becomes an integral with just t and the gradient of a power of u. Gradient of a power of u, this we know how to compute. It's the chain rule. And this will be some coefficient due to some power, gradient u. At this point, we can rearrange the powers here using the definitions. It takes this simpler form. P star divided by P prime, that's the exponent, where P prime is Lebesgue conjugate to P. And now, I will apply another fundamental and basic inequality, which is Hölder. And separate this in gradient u integral and the t integral with u to the p star. This is Hölder with conjugate exponents p and p prime. And the last thing I will do is do again a change of variables here to replace this integral with respect to u to the p star by the integral with respect to g. Okay, just a few lines. Now see here how amazing. This depends only on g, doesn't depend on u. This doesn't depend on u. So only dependence on u is on this. And this shows that this LP norm of gradient u has to be bounded below by a constant. And so you have your relation. You can, by the way, optimize with respect to g, do many things. And this method is quite subtle and was pushed, for instance, by other researchers, in particular Figari, Maggi, Pratelli, to prove very subtle, well, subtle is a perimetric inequalities with error terms, with remainders, precise inequalities. For the Wolf is a perimetric inequality in which you replace the Euclidean norm by an arbitrary norm, and then the solution of the isoperimetric problem is also the ball, provided that in the surface integral you take into account the dual norm of the unit normal. It arises in some variational problems coming from physics here and there. And we have just the same isoperimetric inequality if I forget about this, it would be the same, like the surface of omega is bounded below by the surface of the ball for any ball which has the same volume as omega. But now if you want an error term, if you know that omega is not the ball, what do you gain? What can you squeeze in? And here they show that you can squeeze in what is optimal, a constant times the square of the relative volume of omega inside the ball, where the infimum is among all balls that you try to fit with omega. This is subtle, and to get this, they used the optimal transport properties. Other unexpected applications of optimal transport popped out in the past 20 years. In fluid mechanics, in dynamical systems, in meteorological equations, in the theory of Monge-Ampère equations, or Boltzmann equation, or sand piles, or reflectors, or image processing, or irrigation basins, or even cosmology. It was quite a surprise, and that was a big renewal of the field. Like in the previous problem here, why would you use optimal transport at all? It's purely geometric problem. There is no such optimal transport. But in fact, you can see it behind. In 2008, I wrote a thick book trying to make a synthesis, comprehensive, of all the subject from the beginning, and discussing these various interactions. Interactions that were maybe the most unexpected came from statistical physics. I will discuss the interaction of optimal transport now with entropy. So far, we saw some relation between economics in the sense of optimization and geometry. Now it will be statistical physics. And this object that is one of the most important functions in statistical physics, maybe the most important, the Boltzmann H functional, or its negative, the entropy. If you have a statistical distribution f, the entropy is defined by minus integral of f log f. This is a magic formula. Boltzmann identified this quantity with the entropy of a fluid whose statistical distribution is f. In kinetic theory, which is a study of gas according to the statistical distribution over position and velocities, the integral is over position and velocities. And the big discovery by Boltzmann was that this quantity can only increase with time. This order becomes more and more pronounced as time goes. This was an instance of the second law of thermodynamics, but what was beautiful is that instead of accepting this law as given, Boltzmann gave a mathematical argument for the law to be true. This was a revolution. The H functional, or the Boltzmann entropy, does not appear only in kinetic theory of gases. It's universal. Boltzmann really transformed this physics concept into a mathematical concept, which then was reused by many. One of those who rediscovered the entropy was Claude Shannon, one of the fathers of modern computing science and the father of information theory. Here Shannon tells us about his rediscovery of entropy and why he used that word. I thought of calling it information, but the word was overly used, so I decided to call it uncertainty. When you see this, you think there's a problem, because information and uncertainty seem to be opposite of each other. But when you think more, you understand what he means. Information that you gain from some signal is important only if there was uncertainty a priori. If you already know in advance what this guy will say, you don't get any information when you decipher his message. So it's the a priori uncertainty that makes the value of the information. When I discussed it with John von Neumann, he had a better idea. You should call it entropy for two reasons. In first place, your uncertainty has been used in statistical mechanics under that name, so it already has a name. This was the same concept. because information in a gas can be to know how much information you extract from the measurement of the position of one particle. If you know that all particles in your gas are confined in a very tiny space, and you extract one particle and you measure and you see it is in this space, you gain no information because it was not uncertainty a priori. But if the gas is very diverse, very much spread, you will gain a lot of information from one measurement, from this disorder. In second place, and more important, no one knows what entropy really is. So in a debate, you will always have the advantage. This was a nasty comment of which von Neumann certainly was very much fond. He was a nasty guy. Trying to put some kind of curse on entropy, but it is, in fact, simple. Simple but very deep. Simple but very deep. And it has been re-obtained in many places, many fields. There is another formula for entropy, which is very well known, and which was also given by Boltzmann. Entropy is a measurement of the volume of microstates associated to some degree of accuracy in macroscopic observables to a given macroscopic configuration. It looks complicated, but it is not. If I observe a system which is made of many things, many objects, I cannot measure the precise state of each of these objects. I can only measure statistical properties. This gives me a partial representation of that object. So a lot of uncertainty remains of all the microscopic configurations which are compatible with my observation. And I can make the list of that. And if the number of possibilities is very small, it's a very ordered state. I will say the entropy is low. If it's very high, I will say the entropy is high. Entropy is an entropic concept in the sense that the value of entropy will depend on how you observe your system. If you are like God and know everything, there is no entropy, no uncertainty. Entropy is a way to measure the ignorance associated to a way you explore a system. And this is the Boltzmann formula. S is k log W. K is a constant logarithm of the number of configurations. This is a formula that is not less important than, say, E is mc squared of these things. Maybe even more because we experience it every day. Here you see the formula on the Boltzmann grave. Boltzmann died in 1906, and in 2006 there was this conference organized in Vienna to celebrate him. So I was one of the lecturers, and I knew he was buried there, so I went there to, meditate over his grave. But this cemetery, Central Friedhof, is a monsterly large cemetery. You arrive there, you are lost. There are some famous people buried there, but without any map, there is no way you find them. So I look for a map. And I see these guys here sitting on a bench. I ask them, do you know where I can find a map? They say, no, there is no map. We already tried. Who are you looking for? And I say, I look for Boltzmann. I think maybe they know him. Who knows? And then the guy looks at me with shiny eyes, and he says, S is k log W. So he knew. And he took me to the grave. And here you see, it's really like, in this example, it's really a magic formula. And it is. So S is k log W, and it's weird though. I gave you one formula and then another one. I told you S is minus integral f log f, and now S is k log W. It really is the same, and this is a beautiful exercise that you can do and without knowing much of physics. It's a combinatorics exercise that was also understood by Boltzmann. And here you really see the idea, the spirit of entropy. You look at the system. What you can measure from a system is maybe a bunch of statistical numbers. Like I can measure, if I have a system divided in small boxes, what's the proportion of particles in this box, proportion in that box, etc. But I cannot measure each particle where it is. So you look at the frequencies, which is a set of observable quantities adding up to 1, and you look at all the possibilities, the microscopic possibilities associated to this observation. So in each box, you look how many particles there are and how many configurations this gives you. If all the frequencies are 0 except 1, there is just one possibility, that is to put all the particles in this box. The number of admissible states, admissible configuration is 1. If there are like 3/4, 1/4, here on this example, 8 particles, the problem is to choose which are the 2 particles which will be in that box. So 8 choose 2, the combinatorial answer. And more generally, it's an exercise to compute that the number of possibilities is n factorial divided by the product of the factorials. Now, this is a combinatorial answer. And if you take the logarithm of this thing and apply the asymptotic formulas for the factorials, you will find that after you divide it by the number of particles, the logarithm will converge to minus the sum of fj log fj, which tells you how much uncertainty remains after you know the frequencies fj. And from this you go there by saying that this is the discretized version of minus integral f log f. See, it's a very practical thing, and in just this quantity, minus integral f log f, Boltzmann has summarized a lot of combinatoric information. It's a deep concept. In 1998, Jordan, Kinderlehrer, and Otto found a beautiful link between the Boltzmann's notion of entropy and 2 other objects that are well known, the heat equation and the optimal transport. Here we'll see an example in which the problems will come together, coming from statistical physics, say, and economics or optimization. This can be set in Euclidean space or on a compact Riemannian manifold. Works just the same. What is this link? This link is a way to solve the heat equation of Fourier by using an unorthodox gradient flow scheme based on time discretization and transport problem. If you know at time t an approximate solution, you look what it will look like, at what it should look like after a time step delta t. And to do this, you optimize a quantity which is combination of the Boltzmann notion of entropy, or h function, plus the transport cost divided by 2 times the time step. So I need in here to do this. It means that each time step I maximize the entropy, but putting a penalty if the transport from the density to the other density is too strong. This is a variational principle, a bit like maximization of entropy. It's a dynamic one. And it's beautiful that the solution, as the time step delta t tends to 0, converges to the heat equation. Also, it's interesting to see that in this scheme, by construction, the entropy increases with time. When you have such a time step discretization procedure, this is known as gradient flow, and it's well known that you can get information about the qualitative behavior of your equation by looking at the geometric properties of your function, your landscape, as they say. So this suggested to investigate the convexity properties of the entropy. but convexity property not in the sense of the usual approximation, of the usual interpolation. Convexity in the sense of optimal transport. That is looking at probability measures as a metric space in which the distance is given by the square root of the transport cost. And the geodesic will be a path of shortest length between two such probability measures. And along this path, you are asking naturally the question whether your function is convex or not. Convexity is always good when you want to study the qualitative properties. And then at the time I was working with Otto, and there was a natural question to ask, what is the behavior of the Boltzmann functional along the interpolation of optimal transport? So you take a gas which transforms according to minimization of kinetic energy, its equivalent. What to say about behavior of the entropy? The answer is not universal. The answer is that it depends on the curvature. Curvature, let us remind, curvature was the great invention of geometry in the 19th century. Some objects are positively curved, and it means geodesics converge faster than they should do. Some objects are negatively curved. In positively curved objects, triangles are fatter than should be. In negatively curved world, triangles are skinnier than they should be. And negative curvature makes beautiful art objects. As here, not the here, here. Here, this is the hyperbolic coral reef that you can find in Dublin. This is hyperbolic coral reef. You knit it in such a way as to obtain negative curvature. Of course, you cannot go far, but you can do a bit. This is another example of constant negative curvature world. In all these examples, the notion of curvature which is used is the sectional curvature. Curvature also changed the face of the world when it was used by Einstein in general relativity, something that we now use daily in our GPS, taking into account the corrections of general relativity which are encoded in curvature. The notion of curvature which is used there is a notion devised by Ricci-Courbastro, based on the Riemann definition, but which is a contraction of it. Recall definitions, a geometric way to get them. Sectional curvature is whenever you have two orthogonal unit vectors in your tangent space to some manifold, the curvature measures infinitesimally the divergence of geodesics with respect to the Euclidean geometry. From this point, I send one geodesic here, another there. These are two unit orthogonal vectors, and I measure the distance at time t. If you were in Euclidean space, the distance would be square root of 2 times t, Pythagoras. In a curved world, there are correction terms. The first correction appears at order 3 in time, and it's proportional to the curvature. Negative curvature, the increase is fast. Positive curvature, it's slow. The Ricci curvature is an average of these sectional curvatures. You look at the Ricci tensor applied to unit vector E in the following way. You put this vector E inside an orthonormal basis. And for any time you can pair E with one vector of the orthogonal basis, you compute the corresponding sectional curvature. And you sum all of this. And then this extends to a quadratic form in terms of the vector E. It tells you something about the way geodesics diverge on average when you look among all directions. So it's associated not really with distances, but rather with surface, average over directions. And you can express it in terms of second derivatives of the metric G. Here, of course, I expect everybody is familiar with the beautiful, okay, mathematicians here are familiar with the beautiful book of Do Carmo, which has become the standard worldwide to learn about this stuff. Now, relation between transport and reaching, what is it? And this is what we found with Felix Otto. Link between the statistics world and the geometric world. You can tell that Ricci is non-negative by looking at the behavior of entropy in terms of the transport and the transport according to optimal transport. The fact that Ricci is non-negative is equivalent to say that the H function of Boltzmann is a convex function of time along optimal transport. Let us comment on this by contrasting two interpretations of Ricci curvature. The classical one would be to say, how do you know that Ricci is non-negative? Well, answer is Ricci is non-negative if you always have a distortion and you overestimate the surface of objects that emit some light. Here is the light source. This is me standing here watching the light source, and the light rays are distorted by curvature. This is a picture of positive curvature. But I don't know this, so when I reconstruct the light source, I overshoot, I overestimate. This is characteristic of positive curvature. On the contrary, the new indication, the new way to see it, that was developed by a number of authors at about this, after us, is the following. To decide if you are in positive curvature, in a negative curvature, you take a gas with a certain distribution with density rho, and you give him the order to change density and you impose the final density, as in the Monge problem. And the gas is lazy, that's a lazy gas experiment, so he will obey you in such a way as to minimize the total energy, minimize the action, to be more precise, minimize the energy which is spent. So this is a variational problem. And all along time, as the gas does this from time 0 to time 1, you measure the entropy, the disorder of the gas, using the formula of Boltzmann. If the curve is always concave, this means you are in non-negative curvature. See here, this statement is equivalent to this one, although it's completely different. And this is interesting. First, it gives you some new link between three fields: Riemannian geometry, statistical mechanics, and optimal transport. Second, it allows you to solve, it has been used to solve a problem, basic problem in Riemannian geometry, having to do with the synthetic notion of curvature. We used to distinguish in mathematics between analytic or synthetic point of view. Analytic is when you compute, synthetic is when you focus on properties. To illustrate this, let me construct two possible definitions of convexity. We all know what convexity means. And you can say that the convex function is a function whose Hessian is non-negative. This is a way to define convexity which is analytic by computing a second derivative. In contrast, we can say that a function is convex if the graph of the function always lies below the chord. This is a property of the function in which we don't compute anything. The first definition is certainly more simple. In practice, in general, this is impossible to check directly. Also, this is interesting because this is local. That means there is only this point x, while here it involves various points. When you see this definition, it's not even obvious that there is a local way to translate convexity. The first here is effective. It gives you a way to compute. But we all know this definition is also very useful. And it's more general because you don't have to differentiate twice to define it. And it's also more stable. Why are convex functions so popular This is because we have these two dictionaries. For instance, imagine you want to prove that the limit of convex functions is convex. If you use this definition, it will not work, except if you know that the second derivative converges. But if you use this definition, it's a joke. Just pass to the limit in this, this, and this. So the interplay between them gives you a lot of power. Now, in geometry, there are also some synthetic analytic point of view. For curvature, a space-sectional curvature non-negative, this curvature non-negative, this would be the analytic definition. But you can also use a property that triangles are puffy as a definition. And this is the famous Cartan-Alexandrov-Toponogov theory. Puffier means what? I look at a triangle in my curved space, and I compare it with the isometric flat triangle. If the median here is never shorter than the median there, this means my space is non-negatively curved. Puffier is very well justified because if you think of the triangle as an individual, this is the neck, this is the belt, and so this is the thigh, the median. And we all know if you are quite big, you need a long thigh because it has to point to the middle of the belt. So this is the way you tell it to the students. Non-negatively curved space is a space in which triangles are puffy. And why do we like it? First, it's funny, but then it's stable, for instance. Suppose I take a sequence of spaces which are positive curvature, and I want to prove that the limit is non-negatively curved. I will not use that, it's crazy. I will use this one, and this will be so easy. I will use points that converge to points and distance that converge to distance. I only need to have convergence of the distance, and it will work. And it's also more general. Think of this space. It's not a manifold. There is singularity. However, it makes perfect sense to say that the curvature is non-negative. Looking at triangles, this triangle here is fatter, clearly, than should be. This is a theory of Alexandrov spaces, which are singular spaces of non-negative curvature. This theory was rather well developed, but then it was an open problem. How to do the same thing for Ricci curvature? Sectional is distances, Ricci is surface. How to do? And the optimal transport gave the solution. Let us turn the property into a definition and define that a metric measured space, not necessarily a Riemannian manifold, has Ricci curvature non-negative if the lazy gas experiment holds true. That is, whenever I take two probability measures, I can find a geodesic in the space of probability measure that is an optimal transport from one to the other, such that along time, the entropy has a concave behavior as a function of time. And I take this as a definition. And you can also make variants like Ricci curvature bounded below by k. It looks a complicated way to state things. But look, this interesting thing. We never use any smoothness. And all we use are what? Convex functions like rho log rho, integrals, distance, which is hidden in the optimal transport. So these are very stable things. And this definition here is very stable. One thing one can check is it's consistent with the weak definition, so it coincides with the usual one if the space is smooth. Also, complicated as it seems, you can work it out. I mean, you can use it to prove some theorems. For instance, if Ricci is bounded below by k, you can prove this, which is called the logarithmic Sobolev inequality, relating the h function to the Fisher information. It's a geometric inequality, a functional inequality with geometric content. And it is stable. It is stable under the weak notion of convergence in Gromov-Hausdorff topology. or to be more precise, measured Gromov-Hausdorff topology, which is the, when John Lott explained this to me, he told me measured Gromov-Hausdorff topology is the Mr. Magoo topology. I don't know if you know this cartoon character who is very short-sighted. That is, if you look at your space from a myopic point, you should see no difference. Below a certain resolution, you don't see the differences. So in more precise terms, there should be some approximate isometry between your spaces. Approximate isometry means it's an isometry up to a certain error, which is very small. And it's onto, it's surjective, up to a certain error, which is small. And on top of this, you add the condition that up to a good approximation, the map push forwards measure to measure. So this is measured Gromov-Hausdorff topology. Very powerful concept. And the theorem that we proved, that was proved by myself and Lott, at the same time by Sturm, is that it's so simple. If you have a sequence of spaces which in the weak sense have Ricci bounded below by k and converges to a limit space, then also the space has Ricci curvature bounded below by k. And no need for convergence of the second derivatives or whatever. So here a solution of the problem, of this geometric problem, took a very stretched way using these statistical physics, the optimization. Also the people from geometry, of course, they were surprised. Why on earth has this entropy going to do with this convergence? It took longer to show that the two synthetic theories are compatible. This was proven by Anton Petruni in 2009. If you have a compact finite-dimensional Alexandrov space, so sectional curvature being bounded below by 0 in weak sense, then also the Ricci curvature in weak sense is bounded below by 0. This is natural because Ricci, we think of it as the average of sectional. But in the weak sense, how to do? The first one is based on triangles, and this one is based on entropy. So you have to work for it. And this direct link was found by Petronin. So there is a direct compatibility between this Sartan-Alexandrov-Toponogov theory and what I will call Lott-Sturm-Villani theory. Okay. It was also used recently to prove amazingly general theorems about the existence of heat flow. How do you define a heat flow on a space which doesn't have a Laplace operator? What Ambrosio, Gilli, and Savary showed is that you just need to have the Ricci curvature bounded below by k in the weak sense that I described. And when you have this, you can define a heat flow on the space of probability densities. And it's equivalent to define it as a gradient flow of minus the h functions of the entropy, that is, like we said, or as the gradient flow in L2 sense of the Dirichlet form. This is a really strong theorem. And just one geometric condition is Ricci curvature bounded below in the synthetic way. Okay, I think I'm already very much over time, is that correct? I think I will stop here, and okay, I will conclude with one last interplay. You see here, I showed on some example that using reasonings that originated the beginning from economics, you can solve some problem from geometry. The converse is less likely. Solving a problem in geometry, what would we do about economics? That's what one could think. But recently appeared this paper by Figali, Kim, and McCann, who were as part of a program on the geometry of optimal transport. And in particular, they were studying the curvature conditions that allow to develop regularity theory for the optimal transport map. And this paper appeared in Journal of Economic Theory, so it has to do with economics. What they discovered is that the geometric conditions allowing the optimal transport map to be smooth also allowed a certain economic problem to be written as a convex program. That economics problem is the multidimensional screening. To describe roughly what it says, imagine that you are a CEO of some company working on some product that we will give to the consumers, and you can have a variety of products, some cheap, some expensive, maybe some options. And you want to know about the dimensionality of the parameters that you will, of the options that you will propose. Maybe you just have one model and you decline it according to the size, this big, small, large, etc. Or maybe you make some cheap ones and some expensive ones, and expensive one more options. How do you solve such cases? And in there plays a central role is a certain function depending on two variables, which is a bit like this cost function we had before. You can think of it as representing the matching between the price, the satisfaction of the consumer, something like this. And you can reformulate it in using some particular equations. And for a long time, people could prove it only when that particular function is a scalar product. And they arrived at this conclusion, which is maybe immoral in a way, that your interest usually is to put really much more options for the rich. That is, you have just a one parameter family for, okay, you don't care about the poor, then you take one parameter family for the middle class, and then a multi-parameter family for the rich. And this is the way you optimize the thing. And with, in particular, the corresponding measure, there is a change of dimensionality of the support. And it was an open problem for quite a time to know if this was a special feature of the scalar product. And McCann, Figali, and Kim, they showed that they discovered a whole class of cost functions for which you can solve this. Exactly the cost functions for which the optimal transport has a smoothness theory that you can build. Unfortunately, they recovered the same immoral conclusion. Okay, that's it. Thank you. Thank you.
Are there any questions or comments? No questions? No? Okay, then let's...
Well, noon 30 is critical time. Everybody is hungry and we work hard. So this I understand if you want to take a break with some terrestrial food.
Okay. Thank you very much then.
Thank you.